Okay, this problem is from 4.7 number 5. This is an unknown radioactive element decays into non-radioactive substances. In 880 days, this is the tricky part, 880 days, the radioactivity of the sample is decreased by 61%. So out of 100%, 61 is gone, so 39% is still there. So we're going to go with the formula. The amount at time t is the initial amount times e to the kt. By the way, there's many ways of doing this. This is how we're doing it from this book. So let's first start off with this 39% figure. So we say 0.39 of the initial amount is the initial amount times e to the k times 880. So we could divide a sub 0 from both sides. And 0.39 equals e to the k times 880. If we take the natural log of both sides, this is how we can get down to this exponential. That cancels the natural log of e. And we have the natural log of 0.39 equals k times 880. So if we divide both sides by 880, we have k equals the natural log of 0.39 divided by 880, and that's our exact amount. To get our approximate, we put in our calculator, and I get negative 0.00107 00097. Now, the amount at time t is going to be our initial amount times e to the negative 0.00107 00097 t. So now to ask, what is the half-life of this? So we do half-life, half of the initial amount is our initial amount times e to the negative 0.00107 00097 t. Again, we divide out the a sub 0. So those are gone. And we have the 1/2 equals e to the negative 0.00107 00097 t. Now, by the way, I kept that number stored in my calculator and I use it for this next calculation. So the natural log of 1/2 is the natural log of e to the negative 0.00107 00097 t. That cancels. Natural log of 1/2 equals negative 0.00107 00097 t. And we're solving for t, so I'll divide by the negative 0.00107 00097. Okay, so these divide out, and we end up with our t, and put this all in the calculator. And I saved that value. I took that value and copied it into this space. So I get time is 647.7952308. And there's probably some round off error there somewhere. It's a little bit slightly different in the answer online, but this is still close enough. So that's our half-life. So our formula is the amount at time t is the initial amount times e to the negative 0.00107 00097 t. And it says how long will it take a 100 milligram sample to decay down to 72 milligrams. So we have 72 equals 100 times e to the negative 0.00107 00097 t. We can divide both sides by the 100. And then we have, I'm not going to worry about reducing this, 72 over 100 equals e to the negative -0.00107000097t. Take the natural log of both sides, because that cancels this e. And then we end up with the natural log of 72 over 100 equals negative 0.00107000097t. Going on to this next page. So t would be the natural log of 72 over 100. And that whole expression is divided by negative 0.00107000097. So I put this in the calculator. I'm going to type in my natural log of 72 divided by 100, close parentheses, then divided by, and I could just push my up arrow. You can't see what I'm doing, I'm just describing it, until I get to the other value, hit enter, and the time would be approximately 307.0103635 days. And that's real close. There might be some round off error on mine or on the problem, but 307.01 should be good enough. Okay, hope that helps to explain how to do this pro.